State University. The topic is Liutex and machine learning-based 3D flow prediction. And we know complex flows, especially high-speed complex flows, are really, very hard to, do the simulation, do the experiment. I think most of the people here actually, has the experience. It's very tedious to do the simulation, experiments, and after we get the data, we need to process the data, analyze the data, and get the mechanics. And then after that, what do we do? Sometimes we need to know what kind of flow it will be later. That's a kind of prediction. And sometimes we also need to change a little bit on the configuration, parameters, boundary, shape, right? And this is also kind of a prediction. And thanks to the development of computers and the related infrastructures, and we can nowadays, do the very high order, simulations to get high fidelity numerical data, and also by the developing of big data and machine learning. Now we can also, have a lot of tools and methodologies for scientific research, especially in fluid dynamics. Apply these methods on fluid dynamics. But it's extremely challenging to use machine learning to do the prediction of the general complex fluid flow directly, because first, machine learning models require large amounts of data for training. Although maybe you do a simulation, collect maybe 10 TB data, maybe 100 TB data for a case, but in the scope of big data, you only collect one sample. So if you want to train a general model, for fluid flows, complex fluid flows, this just it's just one sample. So we need a huge amount of data, and also for the complex fluid flow. So vortex can appear everywhere, and we have tons of different scales. We have the shock waves. We have a lot of very complicated, phenomena happen in the fluid flow. So we need actually almost infinitely many parameters, for the neural network, model. So this is far from the number of parameters we need for a large language model. So for the direct prediction, I think it's impossible. And another thing is, we need to talk about the efficiency. If we do the simulation, we only need 1 day. And if we use a lot of data to do the machine learning prediction, we need 1 year. This is useless, right? So this is the method we proposed. It can be divided by 3 steps. And the purpose of this is not to train a general model, but it should also be a little bit general. And also, we do the real prediction based on small data. But as a neural network model for the nonlinear relationship, we can use a lot of data. But once the neural network model for the nonlinearship among the variables, once it is trained, we don't need to change it. We only need to change the model which dominates the flow. So the first step is we use matrix decomposition methods like POD, PCA, non-negative matrix factorization to decompose the large coherent vortex structures into some basic spatial modes or time coefficients that characterize the temporal development. And in addition, we can also eliminate the small scale that is not used, very important to the flow. And the second step, we use the neural network, to do the time series prediction, and for the development, of the vortex structures in the future. And we use the neural network model to do that. And also combining the predicted time coefficients and the spatial modes we got from the matrix decomposition, we can do this kind of prediction or recovery of the development of the major coherent structures in the complex flows. And the third one is based on the prediction of the dominant variable like Liutex. For these complex flows, we can see clearly the vortex dominates this flow, right? If we only need to choose one variable to resolve, I think, of course, it should be the variable related to vortex, right? So here, the matrix composition method, we used it to, and also the second step, for the prediction, we used to, get a model to do the prediction of the dominant variable, like Liutex for the vortex. And for the other variables, like the velocity, pressure, we can train another neural network model. Okay, and for this model, because we don't need to change the parameters, once it's trained, it's over there. It could be more general. Okay, we use this second neural network model, to get the prediction of the other variables or parameters. So this is the illustration of our proposed method. So the first step and the second step, it belongs here. And the third step, it is this. So this predicted dominant variable, here we use Liutex, it is based on fast prediction. So this kind of machine learning training, we can only use small data to ensure that our actual purpose is use this prediction framework to do the real-time prediction, like for example for the real-time flow control, right? So we cannot use a lot of data, we cannot use a lot of computing resources to do this this kind of fast predicted variables. Okay, but for the nonlinear shape among this dominant variable and the others, the other information like boundary conditions, like different parameters. Okay, now we can use a lot of data, as much as we can, and we can train a neural network model, especially for the nonlinear relationships, and combine these two, we can recover or predict the whole fluid flow. So this is our proposed method. Okay, so for the matrix decomposition, we tried a lot of methods, and we prefer to introduce the POD or PCA and also the non-native matrix factorization. We think these two methods actually did the best job. So for POD or the general PCA, if we have the snapshot matrix, right? If we put all the numerical solutions to form a snapshot matrix, and we usually for the larger scale snapshot matrix, we do the SVD, right? And based on the formula of the covariance matrix, we can get if we do the decomposition, we can get first the spatial modes, L times this, L is the left singular matrix, sigma is the diagonal matrix for the eigenvalues, R is the right singular matrix, right? So the right singular matrix, it is it can be considered as time coefficients for L times sigma for the spatial modes. And for the non-native matrix factorization, it's very similar. We have the import matrix. The import is the snapshot matrix, and we can also decompose it to a matrix for the weights, and then another matrix for the coefficients. This method is first, I think, used in image, processing, like, this I give here. If we have a photo of someone, then we decompose it to facial features, and also the importance, the coefficients of weight, of these features. And if we combine these two matrices together, we can also recover the original matrix. But of course, in this process, we can ignore some, small features, not used features. We can also, in the process, we can also eliminate the noises. Okay, so this is the test data because we want to apply it for the flow control, real-time flow control. So this data actually is from our previous, LES of MVG controlled high-speed flow. MVG, generate, this kind of, vortex structures. Why we choose this? Because first, we want to apply it to the, active flow control. Secondly, the flow, this vortex structure is not too complicated, but it's not simple. And the third is, it's a little bit, periodic, but it's not periodic because the import we have introduced a lot of noises. So yes, for the test data, we want, we need to, evaluate the efficiency of the method. So we want it to, be done, as soon as possible. Okay, but for more complex flows, we need, of course, keep more information and then more computing power. And for the matrix decomposition framework, we first, form this snapshot matrix, okay, and then we also investigated whether normalization plays a very important role. And then, we use different matrix decomposition method, POD, and non-negative matrix factorization. And also, we want to do some optimization on it, so we use different variables. So exactly here, we cannot claim it is POD. POD is usually for the velocity, right? But we use the Liutex, we use the original, velocity, we use the density, and also include the energy, and we also tried, combine, different normalization methods. Okay, out of that, we got the modes and then try to do the reconstruction and it's compared to the original data. And these are the normalization methods we used. We mainly tried min-max and z-score. And these are all the cases we did. Actually, we cannot claim this as the POD. It should be more general, PCA. Okay, Liutex, the 3 components or 4 components, adding the magnitude and the Liutex with mean centering, min-max scaling, and also the magnitude of Liutex using non-negative matrix factorization. Okay, so let's compare it, with this. Result from simulation. This is the isosurface of Liutex of this vortex structure at the time step equals 200,000 steps from our simulation. And here are some modes we got from different cases. This is the first 6 modes from the case we use PCA and the 3 components of Liutex with the mean centering for the normalization. And this is the magnitude of Liutex with non-negative matrix factorization. So we mainly compare these 2 methods because these 2 methods are quite different. POD or PCA give us the spectral based modes, and the non-negative matrix factorization give us the characteristic-based modes. You can see, these modes from POD or PCA like sine or cosine waves, right? And the second non-negative matrix factorization, actually it decomposes the real, vortex structure. For the this vortex structure, we have ring-like vortex and also the 2 span-wise rotating, string-wise vortices. And the non-negative matrix factorization actually it decomposes it to be parts. And then we do the reconstruction and to evaluate the results compared with the original data. And we can see that mostly we can get the coherent structure back very well, except that we have some pseudo vortices. These results are from POD. For POD, like because we get the spectra based modes, right? So if you only keep some of the modes to do the reconstruction, then you will have trouble to the negative values. You cannot eliminate these. So these are this is the cause of these pseudo pseudo vortices. But if you have more modes to be included in the reconstruction, these pseudo vortices can also be eliminated a lot. And for the non-native matrix factorization, actually we don't have this trouble. Yeah, so you can see it's very clear. The first one, we don't have any pseudo vortex. And if we use velocity, we have a little bit, but it will be smaller. And also we evaluated the mean square error. What's the actual error? If we only use the first 40 modes, to do the reconstruction, to do the decomposition and the reconstruction, we can see the mean square error is quite little. And also, for all of these cases, they are in the same order. POD, PCA, and with different variables, and also non-negative matrix factorization, almost in the same scale, same orders. The error is in the same order. So here are some conclusions we made, so far for the decomposition. We compared a lot of, decomposition method, and we tried a lot of different normalization, use different variables. So these are the conclusions. First, the POD PCA gives spectral modes, while non-negative matrix factorization gives the characteristical modes. And regarding constructing vertical modes, we have trouble with velocity involved modes because the modes are for velocity, not for vortex, right? So usually if we use the modes to recover the vortex structure, we will get something like that. So according to this, we suggest to use Liutex for the decomposition. And also we found the normalization and rescaling, actually these do not play a very important role in the decomposition and the reconstruction. And also for non-negative matrix factorization, it is quite good. There's no pseudo vortices. And we only need to use the magnitude of Liutex. Okay, we don't need to use all the three components. Okay, now after we decomposed the information, right, we use small data. Okay, so here for the decomposition, the data set, we only used 181 data files from our simulation. Totally, we generate, I think, about 20,000 or even more data files, but we only used 181. Okay, then we need to do the time series prediction for the flow happen later, right? So how to do that? Matrix decomposition give us this. The first one is the modes. The second one is the related coefficients, right? Then can we consider these coefficients as time series and use some time series prediction method to extend these these coefficients to more columns? And then if we multiply the same modes to this extended columns, then we get the new data. These data actually are the numerical data in the future, happen in the future, right? So this is the illustration of that. First, we ravel all the data variables values into a very large snapshot matrix, and then we do the decomposition, and we get the modes, we get the time coefficients, and then we use a neural network model to do the time series prediction. And after we get the extended time coefficients, we combine it together and get the predicted dominant variable. Okay. And for the time series prediction, we first used the traditional statistical models. we find really not good because for these models, the time series may be very complicated. And also we tried to use traditional recurrent neural networks. We also made some problem. And later we tried the the improved, RNN, it's, long short-term memory. It works. But the problem is for these neural network models, they need a lot of data. Okay, but here as I said, for the dominant variable, we can only use small data. Oh, sorry. Yeah, so how to do that? We use the open source model Moment, and it is a pre-trained model, and we only need to import our time series for the fine-tuning. And here shows the results. We choose some spatial modes, and this is original time series. We have trouble for the traditional statistical methods. These are just the first 6. We can see that the 5th one, it meet the problem, right? And then we try the Moment, and it works quite well. The left is the coefficient from POD or PCA. The right is from non-negative matrix factorization. And then we, for this time series prediction, we totally have 181 data files. We used the first 161 for the training and the rest of 20 for the validation. And here is the result for the validation. These are, compared with, simulated data, except some pseudo vertices, almost the same. And here, actually, is the animation. So first 20 figures are from simulation, and then the last 30 figures from prediction. We can see it's a smooth, very smooth connection. Okay, so then after we predicted the dominant variable, use very small data, very fast. Okay, then how about the entire flow field? For the entire flow field, if we use the Liutex, as the dominant variable, we need to do the Liutex dynamics. While here we don't want to use the traditional mathematical models, we try to use the neural network model. So why we choose neural network model? Because the neural networks are particularly powerful for capturing nonlinear dependencies, right? And we first try the 1D profiles, like these 1D benchmark cases. Okay, we use the very simple ANN, artificial neural network, for 1D cases. And for 2D, we use CNN. And 3D, it's ongoing work. We are doing 3D CNN or high-dimensional time series, but currently we don't have the result yet. And for 1D cases, we use the very simple ANN with only 2 or 3 hidden layers. And you can see the result. Actually, it's quite good. If you want to get more accuracy, you can use more hidden layers. But here we only need to, to investigate whether it can do this. Yes, it can. Like this Schuasche problem. The pressure and the rho, they are totally different, right? But we can also get the prediction very well. And we also tried the 1D profiles from 3D simulations, like this DNS flow. Yes, so I think Dr. Liu's group showed a lot, result for this DNS. We compared the average, velocity profile, 1D, average velocity profile. You can see matched quite well. Use a very simple, super simple AN, fully connected neural network. But for the 2D and 3D prediction, we cannot use AN. We can, in theory, but if we use AN, then the computing cost will be too much. So we'd like to, turn to the help of some methods, developed for computer vision, like CNN. CNN, this is the general CNN, usually used for classification. It is connected with a fully connected, neural network, right, to do the, to do the classification. But for our prediction, the output will be the 2D distribution, 2D or 3D distribution of the variable. Output should also be the 2D or 3D distribution of the variables, right? So we use this newly developed unit architecture. Okay, it is based on CNN, and also we changed it a little bit. Okay, we used a compact unit-like architecture for that, and the input, it depends on the decomposition method. If we use non-negative matrix non-negative matrix factorization, we only have one input, that is the magnitude of Liutex. If we want to use POD or PCA, we use the vector of Liutex. We need 3 inputs, 3 layers. Actually 3 channels, right? So this is the result we get. For the we try to do the these cases are from the 3D results. We cut the the 3D domain into 2D cross sections, and we use these 2D cross sections to do the chaining prediction. And you can see the first 3 actually for U. Yes, so the first column actually, from the the 2D distribution of U and V from the simulation, and the second column from our CN prediction, and this third column as a error. Here the error is in the order of 3, but this is on purpose because we want to we don't want to spend a lot of time, and also we don't want the result to be overfitted. So we just choose a very high, very high tolerance. So you can see, after we predicted the dominant Liutex distribution, at least we can get the velocity back. Okay. So yes, very quickly, the conclusion, because it's still an ongoing work, and it's also in its very early stage, this framework. So I'll give a very short conclusion. First, machine learning 3D evolution of the coherent robotic stage investigated, and the obtained results demonstrate the ability of this method. And with more, suppose if we have more and preserve more modes, it is expected to have better prediction. Liutex here is used for dominant flow, flow variable, because we can see that vortex actually is a dominant variable in these very complex flows. Right?